Pluto, a far-off and puzzlingly small planet, was once a member of our nearby planetary family's planetary system. However, later revelations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a stunning discovery. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating celestial phenomenon, or is there more to this impending cosmic calamity? Join us as we explore the potential consequences of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet due to its irregular orbit, remains a subject of interest and study in the astronomical community. According to recent projections by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Both astrophysicists Neil deGrasse Tyson and Michio Kaku are raising alarms about a potentially catastrophic collision between these two planets, a collision that could pose a massive threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. This means that, since its discovery in 1930, it has not yet completed even one full revolution. However, the intrigue doesn't stop there. Pluto's path is marked by its highly eccentric shape, straying far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination, tilted at 17 degrees to the ecliptic plane. This steep angle makes Pluto's trajectory much more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we might expect from their positions in the planetary system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out due to its steep inclination and unpredictable shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space physics involves understanding how three objects in space, like Pluto, Neptune, and the Sun, move and influence one another with their gravity. It's akin to predicting their future positions based on their starting points and mutual gravitational pulls. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity interact in a highly complex way. Terms like asymptotic libration and apsidal libration, along with the VSK oscillation, are crucial to understanding this phenomenon. According to astrophysicists, what's keeping Pluto and Neptune from colliding is a form of libration. For Pluto and Neptune, this term implies that whenever Pluto crosses Neptune's orbit, their positions are always at least 90 degrees apart. This spatial separation is critical in preventing their orbits from overlapping. Apsidal libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated far above their orbital plane. This provides an additional layer of protection against potential collisions. Another essential factor in this situation is the VSK oscillation, named after three scientists VSK and LV, who studied the movement of objects in space. This term describes how three celestial objects like Pluto, Neptune, and the Sun influence one another with their gravity. This gravitational tugging impacts their motions. For Pluto, the VSK oscillation explains why its orbit near the Sun is so unique. Despite the apparent chaos, this oscillation maintains Pluto's orbital stability over incredibly long periods. The VSK oscillation reveals that although the movements of celestial objects in space might seem wild and irregular, certain patterns and rules keep everything in order. These factors help stabilize Pluto's orbit, ensuring it neither collides with Neptune nor strays off course. The three-body problem further elucidates how orbits evolve due to the gravitational interactions among celestial objects. Studying this helps us better understand Pluto, our solar system, and even distant stars and planets. Numerical simulations conducted in the late 1980s revealed that, despite these consistent properties, Pluto's orbit is inherently chaotic. Minor changes in initial conditions can lead to massive differences over long periods. Nevertheless, these remarkable properties of Pluto's orbit have been found to maintain stability over astonishingly long timescales. Modern computer simulations have also shown how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune, in particular, has a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit. However, Neptune isn't the only stabilizing force. Jupiter's gravity also plays a significant role in safeguarding Pluto's orbit. Helps too. These tests show that Jupiter's gravity alone is sufficiently strong to guarantee Pluto stays on a stable, consistent path for an unbelievably extended length, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are cooperating to ensure Pluto can move securely through space without running into trouble. These qualities are significant in the larger context of the universe for maintaining the control and consistency of celestial body movement. Without these factors, the nearby planetary system, as we know it, would be a place of far greater turmoil and unpredictability. Bodies like Pluto could collide with others or be thrown away from their stable orbits, leading to cascading effects on other celestial objects. For Pluto, particularly with discussions about it potentially colliding with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the dynamic nature of the nearby planetary system. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve harmony through the intricate interaction of gravitational forces and orbital mechanics. It also highlights the importance of constant observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space frequently forces us to confront the unpredictable nature of celestial objects, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using computer simulations has been incredibly helpful in unraveling how Pluto moves through space. These simulations use complex mathematics to mimic how Pluto, along with other celestial objects like Neptune, exerts gravitational pulls on one another. By adjusting small details in the simulations, astronomers can observe how even tiny changes can have a massive impact on Pluto's ultimate trajectory. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite having stabilizing mechanisms, such as asymptotic and scope libration, its orbit can still be wild and irregular. If you start with even a small difference in Pluto's position or velocity, its trajectory over many years can look completely different. Nevertheless, despite this chaos, Pluto's orbit remains stable for extended periods, billions of years. This means that Pluto's journey around the Sun has a kind of order to it, even though it seems chaotic at first glance. Predicting large-scale events, particularly those involving tumultuous orbits like Pluto's, presents significant challenges. The inherent unpredictability of such systems means that long-term predictions are often fraught with uncertainties. While numerical simulations provide a powerful tool for understanding and forecasting the future behavior of celestial objects, they also underscore the limitations of our predictive abilities. These models rely heavily on the precision of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to drastically different outcomes, making accurate predictions an overwhelming task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made tremendous strides in understanding space, Pluto's case serves as a reminder of the limits of our knowledge about the universe. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can have sweeping effects, influencing the stability and trajectory of other bodies within the system. So, why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune, despite these intricate forces working to prevent such an event? Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our nearby planetary system, particularly the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides sharp commentary on the evolving nature of celestial mechanics and the public's fascination with the uncharted realms of space. Tyson's position on Pluto's reclassification is grounded in the ever-expanding knowledge of our solar system. He views the renaming not as a demotion but as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He not only considers the complexities of Pluto's orbit but also its interactions with Neptune, acknowledging the quirks of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still need to discover about the forces shaping our nearby planetary system. In conclusion, Pluto's orbit is a fascinating case study of the complex interplay of gravitational forces within the solar system. While its path is stable for now, the intricate dynamics between Pluto, Neptune, and other planets suggest that even the most seemingly stable orbits can evolve over time. As astrophysicists like Neil deGrasse Tyson continue to investigate the mysteries of the universe, they help us better understand the delicate balance that governs the movements of celestial bodies. The potential for a Pluto-Neptune collision is not necessarily inevitable. However, it's a reminder of the constantly evolving and unpredictable nature of the universe. Despite the scientific theories surrounding Pluto's orbit, it's essential to consider the broader implications of these dynamics for our understanding of the solar system and the universe at large. Pluto's journey is not only one of intrigue but also a reminder that the universe is filled with hidden complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a crucial piece of the puzzle. This resonance, where the ratio of Pluto's orbit to Neptune's is 2:3, is a remarkable feature of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This ratio ensures that, despite their crossing paths, the 2 planets never collide. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic impact.